Hello, everyone. Jared here. If you are new to the stream, my name's Jared. I already said that. Computers bend to my will, but only because I use Ruby, a language notorious for bending when perhaps it should break. I run an agency called Supergood, where we build e-commerce websites using Ruby on Rails, and a framework called Solidus, which is, in my opinion, the most flexible e-commerce platform around. Today we're doing we're not doing e-commerce problems. We're doing advent of code problems. And excuse me, I have the hiccups. We're going to be on day 14 of the advent of code, but it is worth noting that last night when I did day 13, I failed to do part 2. And I wanted to just briefly speak to that. So I had a solution that looked a little bit kind of like this when we left off last night. So if you just watched the video or you want to go watch it, you can watch it on my YouTube. But we had an idea. So we had to find a number such that maybe it's best to just pull up the day 13 input. We had to find an index. You can ignore this first number, a number such that it was a multiple of 17, and then that number plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 was a multiple of 37, and then plus 12, 13, 14, 15, 16, 17. That number would be a multiple of 571. Now, this is analogous to a Chinese remainder theorem problem. I was not, excuse me, I was not familiar with Chinese remainder theorem when I tackled it and got stuck. So if you do it naively, if you just search the space, even if you do it a little bit cleverly, so say you decide you're going to search the entire problem space, jumping by multiples of 17, because you know that the first digit the base number has to be a multiple of 17. You'll never get there, or you might if you use a much faster language, like a C or a Rust. You might be able to come up with something that gets there in an amount of time that you know. It's not ridiculous, but the solution is in the hundreds of trillions for me anyway. So that would take a long time, and it would take a prohibitive amount of time in Ruby. That's one of the spots where Ruby does not bend. is the perf. No, you can always shell it to C. You can make it bend. I came up with the idea that we'd search for an index where we go in steps in 17 and we'd search for an index where both of these constraints were satisfied. And this is where I got off track. It didn't feel quite right, and I'm not amazing. Like, my modulo math and properties of prime numbers are a little rusty, but I couldn't figure out. I knew that once I had a spot where two constraints were satisfied, that I could change the step by which I was looking in order to find, or in order to reduce the problem space. So every time I found a number that satisfied another constraint, then I could use that information to shrink the problem space. And I was right about that, but I wasn't. I really struggled with what I was supposed to do to the step. I tried a few things, they didn't work. I tried setting it to the index, that sort of made sense in my head but didn't work. Turns out every time you find an additional constraint, what you can do is multiply the step by the number that you found, the ID of the bus, the interval. And so once you found this one, you sort of, as soon as I did that, it generalized. So previously I was treating the first bus differently and then doing some special stuff. As soon as I realized that this is what I was supposed to do, set the step to 1, set the index to 0, and then for each bus, for all the buses we've seen, make sure they're like step until we find until that constraint is filled, and then multiply our step by the number of the new constraint that we just solved, and repeat the process until you've done so for all of the buses, and that gets you a solution. And that runs fast. I think it takes about a third of a second or something in Ruby to compute this. I think this is in the trillions. What is this? Thousands, millions, billions, trillions. Yeah. So that it's a number in the trillions that we computed relatively quickly using this method. You can also make some like kind of fun optimizations. So rather than start with the smallest, or rather than start with the first constraint in this bunch of constraints, we can solve them in any order we want. So we could sort them by their IDs. We need descending. And I mean, I'm sure this is now faster. Who knows if it's meaningfully faster. Looks slower. Interesting. Not significantly different either way, but the numbers are going to grow so quickly that solves it pretty fast. This is sort of like iteratively finding, like this is like iteratively doing a Chinese remainder theorem problem. You can do it in like effectively big O one time, sort of. Like technically there's extra math the more constraints you add, but like not meaningfully. It's like I guess technically it would be like big O n or something, because you have to do more multiplication, but like not a significant amount. It's the kind of one where the solution where you just employ Chinese remainder theorem is like trivial. Like I can show you Chinese remainder theorem. We want Ruby. Oh, perfect, we got it. Rosetta code. So yeah, here's some math sort of explaining what we're doing, but basically you pass in the mods, which are the bus IDs in our case, and the remainders, which is their offsets from the number that we're looking for, I believe. And then the actual code for it is trivial. You multiply all of the numbers together. You multiply all of the mods together. You zip together your remainders and your mods. So that's pairwise pairs up the elements. And then you map them to a range, and then you look for elements, the elements they have in common, and take the first one. So that's one of those things where the math just works because the math works. Like, there's a proof out there. I don't fully understand why that works, but I do intuitively understand the approach that I took iteratively, and I kind of, it makes sense to me that this is doing the same thing, just in a simpler way, but I'm not there yet. I'm gonna have to play with it or do a little more reading. But yeah, there we have solved day 13, part 2. So we're set to tackle day 14 when it goes live in 3.5 minutes. As usual, I have some whiskey that I'm tasting. I believe this is Scotch, and we can go take a look at what it is. Tullibardine the Murray. Yep, it is a Scotch. Strange distiller, some of their product can be so good and some of it's so bad. They get some really interesting notes on the nose that I don't get. I get like cherries and paint thinner. I don't get grapes. I don't get the grass. I do get the dried fruit, like the cherries or something like that. Figs, sure, yeah, something like that. And I get a lot of it on the finish. Yeah, it's a little iffy. Not sure how I feel about it. It's pretty good though. This is our dirty. Rocking my Proto Men shirt here, as you do. If you haven't checked out the Proto Men, they are a Mega Man themed band, I guess. Their albums are concept albums and they're very good. Mamesy. Cherry nose, sour cherry finish, dark cherry finish isn't listed. Definitely a very cherry Scotch. Yeah, I mean, I agree with that. That's what I'm getting. Big thanks to Ignoble Solid, who rated us yesterday as we were finishing up my catch-up stream in the afternoon. Brought by some friends to see me finish off day 12. It's kind of fun. Went back and watched his stream, and I think he called this a super tiny channel. I definitely can't disagree with that. Super tiny, but hopefully super good. 45 seconds. Here we go. Let's see if we can fare better than last night. Queue up our command. What's that? We don't need that. Day 14, docking data. As your ferry approaches the seaport, the captain asks you for help again. The computer system that runs this port isn't compatible with the docking program on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the Seaport's computer system uses a strange bit mask system in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program can either update the bit mask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. For example, ignoring bit masks for a moment, a line like mem8 equals 11 would write the value 11 in memory address 8. The bit mask is always given as a string of 36 bits, written with the most significant bit, representing 2 to the 35, on the left, and the least significant bit, 2 to the 0, that is the ones bit, on the right. The current bit mask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. For example, consider the following program. This program starts by specifying a bit mask. The mask it specifies will overwrite 2 bits in every written value. The 2's bit is overwritten with 0, and the 64's bit is overwritten with 1. The program then attempts to write the value 11 to memory address 8. By expanding everything out to individual bits, the mask is applied as follows. Sure I follow here. So because of the mask, the value 73 is written to memory. Address 8 is written to memory address 8 instead. Then the program tries to write 101 to address 7. What? Oh, okay. So we're assuming that the value in memory was all zeros. And we write this with this mask. So the 1 goes through, this one doesn't, it's replaced with a 0. This one goes through, and okay. Then the value 73 is written to memory address 8 instead. Then program tries to write 101 to address 7. So that's decimal 101. The mask is applied. Then we get some other value. Sign the mask has no effect as the bits it overwrote were already the values it tried to set. Okay, finally, the program tries to write 0 to address 8 and instead writes 64. Yes, I understand that. To initialize your fairy stocking program, you need the sum of all values left in memory after the initialization program completes. The entire 36-bit address space begins initialized with 0 at every address. Yeah, that's the assumption I made. I feel like they should have said that earlier. In the above example, only 2 values in memory are not 0, 101 at address 7 and 64 at address 8, producing a sum of 165. Okay, that makes sense to me. A little peek at the input. So the mask changes. We want to do like another immutable, thing that I did before. I already did that part. So let's generate day 14, open day 14 Ruby, open day 14 text. Trying to type too fast. Okay, this isn't even that. 545, easy, no problem. All right. So I want to be able to parse these inputs into structs, I guess, maybe. Class methods? Anyone for some class methods? So we need two types of, we need a mask instruction. And we need a write instruction. And let's grab our test here. Can I do this easily here? Yeah, I must be able to. Okay, so we do that. Then we def test sample input. And make sure we stay hydrated. So this is going to be an array of things. It's going to be a mask instruction with, we'll just use this as a string for now. And then we want a write instruction, and those ones we will use numbers. Oh, but okay. Those need to be converted from binary. Oh, we can do that though. So, oh wait, these are decimal numbers. They just use them as binary to confuse us. Yeah, decimal 11. Very confusing decision, but okay. So these are decimal numbers. And that's a test. That's what I was worried about. Okay, let's do a real class. It's not going to be stateful, so okay. We get nil because we haven't implemented it. We go input dot split on new lines, and then we map if line I guess we can just do this. That's a simple way to do that. Thanks for the follow, it's Indy. Welcome to the channel. Just working on advent of code again. I'm just gonna put 0 values here and make sure we're sort of on the right track. So if I'm here, that means this is a mask line, and if I'm here, that means this is a mem line. Cool. That is what we expect. So now we can pop a regular expression in here. Mask equals, and then we're going to capture some number of x's, ones, or zeros. I guess we know how many. There's 36 of them. Yeah. So that match did not work. Which is interesting. It is 36 ones and zeros. Okay. Tubular. No reason to try and manually debug that in a REPL. Pop that in there. Get ourselves a nice test input or two. And so presumably this is the piece that's not working, because that's going to work. Do you have experience with WebDev? I'm new to it and need help trying to put more text below my existing text on the site and don't know what commands I should use so that I don't have a bulleted list on the side of the screen. I am in fact a professional web developer, but little tough for me to help you in this context. With that. I mean, bulleted lists use the UL, the unordered list element. You probably just want your context in p tags, which are for paragraphs, something like that. Okay, what am I doing wrong here? That's not even matching. Oh, I wasn't supposed to escape these. I'm using like Vim regular expressions or something. Gah. Okay, 1x 36 is the regular expression I needed. Okay, cool. So solve that. So that should give us match. Perfect. That allows us to extract the string easily, and so we can move on to the other case. So we want this to be mask inst. If you want to use UL tags without bullets, you'll want to there's a list style type CSS property which controls the bullets. All right, so that's that covered, and then our other case is gonna. I think I can probably just. So we've got a line. We want to match on that line, and it's gonna say mem, and then we want to capture some number of digits. And then capture some more digits. Nope. Is D not? D is digit, yeah. Oh, I need to escape the square brackets. There we go. That's what we need. Wow, I am typing the wrong disable pry all the time here. All right, so we can use that. We say match equals, and then we can construct our write instruction with match one, convert that to an integer, and get the other match as well. Convert that to an integer. And now we have something that is not passing, but looks kind of like it should. Where are we differing? Glad you figured it out. Thanks, yeah. I've got pretty good camera, pretty good connection, so it's my computer struggles. I'm always using all my CPU, but so getting 0 was the last one, which is correct here. I mean, I'm on a Mac Mini with a Intel i5. It's mostly because my programming environment is actually running on one of those new M1 MacBook Airs, but the lack of a GPU makes makes it a little taxing on the CPU. I normally have an eGPU I use, but it is on its way back to me from getting repaired because it had an issue with its fan. Its fan made far too much noise. Okay, so our parser is written. We can now work with this. However, I don't think I think we've got an issue because I don't know how I'm going to use this bit mask. Big Bears fan. Oh yeah, yes, yeah. I'm a Cubs fan. I'm Canadian, but the Cubs were the first MLB team I got to see live in Chicago. It was their last game of the first 100 years at Wrigley, so it's kind of an exciting game, and ever since then that's what got me into baseball. Nice. It's nice to get into nice to become a fan at least a little bit before they broke the curse. Yeah, it was big. Bunch of Cubs fans in my office. So at the time, we all sort of took over the boardroom and always had the games on during the run. Now, don't exactly know how I'm going to implement this. Yeah, Swiss cheating. Yeah, I mean, it sucks. There should be more I mean, I don't. I don't have cable, so I don't watch sports. I don't follow sports super closely. I'm not a fan of it, and I don't think the league handled it very well. If they want to deter people from doing that kind of stuff in the future, but it's also hard to know without knowing what was going on behind the scenes. So I am going to implement this sort of like I've implemented previous ones and do a sort of immutable machine type thing. I guess I can do the other syntax, machine equals struct new, and then it has, nah, I think we're just gonna do immutable. Let's not overcomplicate this for ourselves. We initialize it with a program, which is going to be a list of these mask and write instructions. Let's save the program into an instance variable. We'll make that available to ourselves. And the result is going to be, we'll worry about the result later. Run bang is going to run the program, but for the purposes of test driving this. Yeah, all too often. I'm pretty good at spotting spelling errors, though. I learned to program in C initially, which is not very tolerant of spelling errors, so I'm kind of small formatting things and things that don't look normal stand out of the code a lot to me. Ooh, I am. What is going on? I'm gonna go bring the MacBook Air closer to me because it's in the living room and I'm getting a huge amount of latency to it. All right, so let's test example. Max CPU upgradable? I doubt it. CPU is not the problem though. The CPU is fine. It's just that when the CPU is also doing the work of the GPU and streaming, that's where the issue is. So that's why I use an eGPU normally. And when I use an eGPU, everything's perfectly fine. All right. So we're going to create a new machine. We are going to execute our first instruction here. Thanks, yeah. I just got this guy. As because the company I run is fully remote and I spend a lot of time on calls, so I do this sometimes, so it seemed worth investing in a really good mic for me. So I'm going to expose the current mask so that I can execute that instruction, and then assert that the mask is now the new value. Okay. So that's not going to do anything. Wrong number of arguments. 39. Well. Gotta give that an argument. Cool. So now we can see that that didn't work, but we can implement this. So we can say case inst when it is a mask instruction. Super good is a, we're a agency that works with e-commerce businesses to build them e-commerce stores and other e-commerce software to help them run their businesses better. We build on Ruby on Rails because it's exceptionally flexible compared to other sort of platforms, and Solidus, the e-commerce framework that we use, is built on top of that. It's really flexible. So we work with brands that need or want a lot of flexibility in what they're doing. They don't want to just use Shopify or whatever. Because, Shopify doesn't meet everyone's needs. It meets a lot of people's needs, but once you get into sort of really custom stuff, you gotta control the code. You gotta be running it yourself. Yeah, I got lucky. I was sort of in the position to the company that sort of, my company does what the company I was working for before they got acquired did. So I was really just picking up the helm after they ceased operating in the same capacity. All right, that works. This is where I'm gonna have to do something tricky. So now I actually have to do something with the mask. So when it's a write instruction, then we have to do something. So, we're going to want to have memory. Memory is going to be I don't want to do this. So I guess we just do it as a hash with numeric indices, and the values are also going to be numeric. What kind of tools do we get working with numbers in Ruby here? Thinking about our bit, we have a bitwise and 9:30, halfway through. Okay, falling a little behind here. Do you like to listen to music outside of coding, like music with words? Yeah, I do. I'm a metalhead. just implementing the mask using just raw numbers seems like it's going to be awkward. Whereas I could just sort of like zip them together and do something. Why don't we write a little class for this? Why not? Class, this is going to be a it's not a byte, it's a word, I guess. And let's test converting. So we're just going to use internal representation of an array of single characters, I guess. That seems fine. So let's def test from int word from int. Oh, let's pick one that's easier, or from the example. Let's use the one from the example. So cert equal word.new, and we know that this is going to be there are now 36 of these. It's not pretty, but we can work with it. We know that 11 is 1, double check this, is 1101, 1101, it's 8 plus 2 plus 1. It's going to, there's a typo down here. After I said I was so good at spotting typos. To figure this one out. Right, I was gonna make this a struct. Bits. Love bits. Okay, int 2s. Then we need to pad it with pad string Ruby. I'm sure there's an easy way to do that. I'll just, yeah. I go on rjust, but same thing. Rjust, what are my arguments? The number and then what I want to pad. So 36 and empty string. Oh, but not empty string. We want zeros, and then we want it as a trying to go too fast. There we go. Cool. So now we can do that, and then that should be as simple as that. Perfect. Test pass. Ooh. Now we're getting somewhere. Now we want to be able to convert these back to integers. So see on my clipboards. Okay, then we can go, we called this field bits. Dot join, and then we want to 2i that base 2. Fantastic. And then I think I want to be able to apply a mask to it. Right? So masked takes a mask and returns a new word that has that mask applied to it. The mask is just going to be a string of x's, ones, and zeros. That's reasonable. Write I'm writing my test in, or my code in the test. So let's test masked, and we want to take our sample word. We want to, what did I just do? Sorry, jumping around a little bit. We can use our example, so we can apply this mask. So we can say word equals word dot masked, and we'll apply that masked. And then we should be able to assert equal it's going to write 73 rather than what we expect. So 73 word dot 2i. Cool. That of course doesn't do anything. So returns nil, and then we 2i nil, which is 0, and then there's nada. So I'm going to I think we can do this we can do this fun way. So we have a mask, we have bits, we can match them up. And then individually, we can map each of these, which are an XY pair. We can say if x equals x, then y else x, which produces a vaguely correct looking bit string. Excellent. So that works as expected as well. So what next? Now we can some other refactorings here. So that all of our instructions are working with these things. Okay. Tests are still passing. Oh, the same thing again. Okay. Oh, and I changed the only one that doesn't matter at all. Okay, let's just copy that. Okay. Still good. We need to make an assertion after this though. So we want to be able to assert that m.memory. Oh, I don't know why. Come on, computer. I wonder if it's like throttling down because it's going to sleep. Memory 8 2i should be equal to 79. What our thing was? 73. Except that's assert equal 73. Boom. Actual 0. Excellent. Okay, so we can implement this now. We can say memory instruction dot address equals instruction dot value masked mask. Hello, come on, computer. And it passes. In fact, we don't even need to pass in a program. I don't even know why I did that. I always like to drive these from the outside anyway, so. I'm going to finish coding this example as a test. We're going to remove this run method because we're not going to use it. But we will need one more method before we are done here. So we've already done those ones. We are going to step. Do that again. We can make assertions. We can make sure we haven't missed anything. So we are going to write decimal value 101 into memory address 7. We are going to write 64 to memory address 8. And change the API, but didn't remove that. Okay, cool. That still works. Refactored that all. And then the final thing is we want to be able to assert that we get the right results. So m dot, what are we gonna call this? Sum is that method doesn't exist. Sum is just memory.values.sum. Memory values map them to integers again. Sum that. And so here we should be able to say parser parse input each do. So each of these is going to be an instruction. Save it in a program even, because we also need a machine, and then oops, just saved a garbage file. So that's probably our results. See if we got the right answer. Amazing. There we go. Day 14, part 1 complete. Let's see if we can get part 2 done. For some reason, the Seaport's computer system still can't communicate with your Ferry's docking program. It must be using version 2 of the decoder chip. A version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination memory address in the following way. If the bit mask bit is 0, the corresponding memory address bit is unchanged. If the bit mask bit is 1, the corresponding memory address bit is overwritten with 1. If the bit mask bit is X, the corresponding memory address bit is floating. A floating bit is not connected to anything and instead fluctuates unpredictably. In practice, this means that floating bits will take on all possible values, potentially causing many memory addresses to be written all at once. Dang. When this program goes to write to memory address 42, it first applies the bit mask. After applying the bit mask, 4 bits are overwritten, 3 of which are different and 2 of which are floating. Floating bits take on every possible combination of values. With 2 floating bits, 4 actual memory addresses are written. Next, the program is about to write to memory address 26 with a different bit mask. I'm not sure I fully understand, but we'll get there. Next, the program is about to write memory address different. This results in an address with 3 floating bits, causing writes to 8 memory addresses. Okay, I understand that. The entire 36-bit address space still begins initialized to the value 0 at every address, and you still need to sum all the values left in memory at the end of the program. In this example, the sum is 208. Okay. So we're doing this. Okay. So part 2 is going to be different. We're going to need a different machine. So first, we don't need to change the solution. So the code that actually drives the computer can remain the same, and we can even pop in our own input, or our updated input, and assert that we get 208 out of it. So that's a start. However, this is all wrong. So let's try and match the example here in our machine driving test. Then we set 42 to be the value 100. And I'll worry about the assertions afterwards. And then we're going to do I guess I should clear these out, makes this easier. In there. We can still assert. And we want 26, 1, and then this is going to be 208. And since we're using the same code as before, that is incorrect, so we will fail. We can run part 2, which currently returns the same value. Now we should give this a different class name, call it machine2, and that is the only thing I think we need to parameterize about this. So we set machine class here. So now we're using our other code. Doesn't change the result because we haven't changed the code yet. Machine 2 can even inherit from machine 1, and then we don't have to re-implement this method, define our adder readers, or the constructor. We can just implement different logic in our step sequence, but I'm still not, I read through it all, but I didn't quite follow, so perhaps some more scratch will help. Version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Immediately before values written to memory, each bit in the bit mask modifies the corresponding bit in the destination memory address in the following ways. Yeah, Mamesy knows what's up. Oh, welcome, Hoth. Congratulations on presumably having finished this already. We are just in part 2. I don't know when. I never noticed us having not 2 viewers, so I don't know when we switched from being Mamesy and it's Indie to Mamesy and Hoth. Now, I'm not sure what so the values that I'm modifying the memory addresses. I remember. So, sorry, I got distracted. I'm just going to implement it as part of Word. Why not? So, oh, computer, come back. I think I think the MacBook Air goes into like a low power mode because suddenly all my latency to it, even though it's like 2 meters from the router, just keeps just like going crazy. Um, test uh, float. I don't know. I don't know what we're gonna call this method. So if we have a word that word equals word dot from int. We're gonna do an example. Oh, sorry. I guess I want to do from int 42, and then we should get I guess I have to do this with a set. I don't know the API for sets. I would normally use contain exactly or match array in our spec, but I can. Oh yeah, that'll work. Match right up with the screen going off. You know, it's very suspect. Now it's just slow though. I don't know. Maybe it is location services or something. From it. So that should fail. Now, what's the easiest way to generate all the combinations given what we got? I mean, recursive function. Do I do recursive function? Is that the easiest way to do this? How do you like today's Scotch, Oth? Get a lot of cherry off of it. Kind of like it. I'm gonna start writing the recursive function and see where I get. So what's the base case? So we want to build up, we want to return an array of strings. So if each one returns, so terrible naming. But here we go. Zed, what's Zed? Let's do N. And this is gonna do recur, float, 0, mask, and then, so we'll say if we'll zip them together, right? Is that sensible? No, I don't think we need to do that. So our base case is when n is bits.length -1, at which point if mask n is x, oh, we can oh, see what's going on. I'll have to look into location services. Nth slot n mask. This returns if mask n is x, then we return 0, 1. Otherwise, we return bits n. Okay, so that's our base case, nth slot, and mask. Otherwise, we want nth slot, no, sorry. I guess we always want that. This is probably a terrible way to do this. It's already 10 o'clock. I feel so close. Always return an array. Recur, float, n+1, mask, flat map, do ops. This is terrible naming. Map. This is obscene what I'm doing. So recur float is going to return partially built binary strings, right? So we want O followed by, is this valid, Ruby? O followed by opt. Oh, that's ugly. did something. So there's that. Oh, I didn't convert it to a set. So for all we know, that worked. Do we just go set.new on something that's not a set? Oh, they're supposed to be words when they come out. Recur float 0 map. Oh, that's masking a thing. B. Word.new B. Okay, we're writing some really bad code, but it also doesn't work, so good. What more could we ask for? How am I even going to read this? Ho ho ho. Convert them back to integers. Hey. Well, that's intriguing. It returns 4 numbers, and they are not the right numbers. Very intriguing. Very intriguing. We got one part of this algorithm right. I was taking the right example though. Let's confirm that. I didn't actually step through it. Maybe 2i, 2s, 2 would help. Yes, good idea, Ha. Thank you. Excellent thinking. So that's going to show us that this converts them to binary strings, or not. That's probably the wrong wording. Converts them to strings representing the binary. These are not. Let's just adjust them as well, because we can. That's not I meant to adjust them. Those were meant to be zeros, not blanks. One of the tricks is I don't know. $26, $27, $58, $59. So let's see, 26 is supposed to be 1, 0, 1, 1, 0, 1, 0. And slot returns. So, how many of these have ones in there? Two of them have zeros. Yeah. None of them should have zeros in their third slot. That's good. They should all have ones in the fourth slot. The fifth slot, they should also all have ones, and I can see already that they don't. None of them do. I did use the right mask. Let's just double check here. Yeah. How could it possibly be? I believe that's the right slot. We know it doesn't equal it. Wow, that was some good typing. So for this one, we get 0 and 1. And this 30 mask. That's right. I called out the wrong. Oops, let's not do that. So for this one, we should get only 1. What am I missing? This is the number 42. The 5th digit is 0. What? Oh, shoot. We're ending? I just not reading the rules properly. Really good work here. I forgot about the rules. I got so focused on this like bit mask floating logic. I forgot all all this other stuff. Okay. That's easy to implement though. Cool. So we just need to modify this logic. So if it's an X, it can be either 1, else if mask n is a 1, then we return only a 1, otherwise we return the result. Disable pry. Disable pry. Okay. was working just a second ago. Did I change something silly? Oh. The test is now only failing because of my debugging code, I think. Cool. Okay, so all that's failing is our machine has not been updated yet to use this new code that I wrote. So we write our mask, and then instead we do word.from inst.address.float mask.each do address, and we write the raw values to address 2i. Oh, one of these. What? Oh. Okay. See if we have solved part 2. Amazing. We solved part 2. Thanks everyone for coming. It's been a pleasure again. I will be back tomorrow night with day 15 or 14? 15. What was this? 14. So yeah, day 15 tomorrow. If you enjoyed, follow me on Twitter, supergoodjared. Follow me here on Twitch, also supergoodjared. You're interested in the e-commerce sites we built? Check out Supergood Software. Supergood.software is our website. Thank you and good night.